My topic is semiconductor and some terms related to semiconductor. So what is a semiconductor? A semiconductor is a material whose electrical conductivity is lies between a conductor and an insulator. Its conductivity increases with the temperature and can be controlled by adding impurities. So the process of adding impurities is called doping. Then we are moving to discuss some terms about semiconductors. So first is conductivity. So what is conductivity? Conductivity is the ability of a semiconductor to allow electric current to flow through it. Generally in a semiconductor, conductivity is due to electric current and holes. Conductivity. Conductivity is the ability of a semiconductor to allow the electric current to flow through it. Generally in a semiconductor, conductivity is due to two types of carriers. One is electrons and second is holes. Then there is an expression for conductivity. We will discuss that later. Then next is charge of a semiconductor. A semiconductor as a whole is neutral. Semiconductors have equal positive and negative charges. Even though free electrons and holes act as charge carriers, their total charge balances each other. Then there are two types of charge carriers, that is majority carrier and minority carrier. Depending on the number of charges, they are classified into majority carriers and minority carriers. Majority carriers means charge carriers present in large number, and minority carriers means charge carriers present in small number. So there are two types of semiconductors as Rimsha mentioned about. What? Intrinsic semiconductor and extrinsic semiconductor. Intrinsic and extrinsic semiconductor. What is intrinsic semiconductor? With no impurities. Made up of only one type of atoms with no impurity. Extrinsic semiconductors means external impurities are added. That means doped. These extrinsic semiconductors can be divided into, that is, p-type semiconductors and n-type semiconductors. P-type and n-type semiconductors. Extrinsic semiconductors, external impurities are added. So in p-type, it is doped with trivalent impurity. So in case of p-type semiconductor, we generally add trivalent impurity, trivalent atoms to silicon lattice or germanium lattice. Trivalent atoms, as the name implies, have 3 electrons in their outermost shell. That is, three valence electrons. Example: aluminium, boron, and gallium. And p-type. germanium or silicon. Here gallium is doped. Unlike the silicon atoms which have 4 electrons in the outer shell, these elements only have 3 valence electrons in the lattice structure. It creates a vacancy where the fourth of the silicon atom would have been. In other words, a hole is created. Therefore, when a semiconductor like silicon is doped like this, it creates an excess of holes in this material. This is called a p-type semiconductor with a tendency to accept free electrons more than a regular semiconductor. Then majority and minority carriers. In p-type semiconductor, majority carrier is hole. Hole is excess, so majority carrier is hole and minority carrier is electrons. This is p-type semiconductor. Doped with the trivalent 3 valence electron. Hole is created. Majority carrier hole, minority carrier electron. Then next is n-type semiconductor. N-type semiconductor. In case of n-type semiconductor, the dopant is generally a pentavalent atom. It has five valence electrons. Example for pentavalent is arsenic, phosphorus, and then When these atoms replace a silicon or germanium atom in the lattice structure, 4 of the 5 electrons are used to create the covalent bond, leaving one extra free electron that is free to move around. This means that N-type semiconductors are excess of electrons compared to normal intrinsic semiconductor. So here excess of free electrons. So free electrons. N-type, majority carries electrons and minority carries holes. It is like this. N-type semiconductor. So these are about N-type and P-type semiconductor. Then next, is the electrical conductivity of semiconductor. In a semiconductor, the current flow is due to the movement of free electrons and holes in a opposite direction. Therefore, total current is the sum of two currents. Consider semiconductor. Consider semiconductor of length L and area of cross section A, and connected to a DC is also V volts, and as shown in the figure, the magnitude of the applied electric field is E equal to V by L. Due to the electric field, both the electrons and holes in the semiconductors are moving in opposite direction. So V is the drift velocity of free electrons. Vh is the drift velocity of holes. Ne is the density of free electrons. And this is the density of holes. total current in the conductor will be I equal to IE plus IH. As the electrons in the conduction band and as in the valence band move randomly like three electrons, so I equal to E N E A B and IH equal to E N H A B H. So I equal to IE plus IH is equal to I equal to E N E A B E plus E N H A B H. EA can be taken as common, so EA into NE BE plus NH BH. This is equation number 1 and this is equation number 2. Now next, mobility. Mobility of a charge wave is defined as the velocity imparted into the unit by electric field. So mobility of free electrons mu equal to B by E, that is BE equal to mu E. Then mobility of holes. Mobility of holes mu is equal to BH by E, that is BH equal to mu H E. So I equal to E A N. E is the inductive velocity of free electrons. BH is the inductive velocity of holes. Ne is the density of free electrons. And this is the density of holes. Then the total current in the conductor will be I equal to IE plus IH. As the electrons in the conduction band and as in the valence band move randomly like three electrons, so I equal to E N E A B and IH equal to E N H A B H. So I equal to IE plus IH is equal to I equal to E N E A B E plus E N H A B H. EA can be taken as common, so EA into NE BE plus NH BH. This is equation number 1 and this is equation number 2. Now next, mobility. Mobility of a charge wave is defined as the velocity imparted into the unit by electric field. So mobility of free electrons. Mu equal to B by E, that is BE equal to mu E. Then quantity of holes. Quantity of holes mu h equal to Vh by E. That is Vh equal to mu h E. So I equal to E A N E V plus N E V plus N H V H. That is I equal to E A N E V is mu E E plus N H mu H. So I equal to E A V into N E mu E plus N H mu H. So this is equation number 3. So we know that E equal to V by L. So I equal to E A V by L N E mu E plus N H mu H. Then 1 by E A L by A into 1 by E into N E mu E plus N H mu H equal to V by I. That is V by I equal to L by A into 1 by E into N E mu E plus N H mu H. V by I equal to R. So R equal to L by A into 1 by E into N E mu E plus N H mu H. We know the equation R equal to rho into L by A. So from this equation rho equal to 1 by E into N E mu E plus N H mu H. Sigma conductivity equal to 1 by rho. So sigma equal to E into N E mu E plus N H. So this is the equation for conductivity. So in conductivity of first conductivity of intrinsic semiconductor. In intrinsic semiconductor, number of free electrons is equal to number of holes. So sigma equal to NIE mu n plus mu h. And in case of extrinsic semiconductor, in p-type, majority carrier is hole and minority carrier is electron. So sigma equal to ENH units. Because NH is greater than N. topic in N-type semiconductor, sigma equal to E N E mu E. Because Ne is greater than. So this is all about my topic.